A good diagram is going to be essential in this question. I mean, look, it just has to be a sketch. It has to look like the original. And we've got this letter S, which I'm going to indicate on the original diagram. So this curved part, then a straight part, and then a curved part, where the arcs, KL and NM, they are 5/8 of a circle. So 360 divided by 8 is actually 45. So I can imagine splitting this up into 5 equal parts, all of angle 45 degrees. The most important one is what is going to be where it hits L. So this angle is 45 degrees. There's going to be a similar thing going on at the bottom as well. Now, if I, oh, and also this is going to be 90 degrees because it's where the radius meets the tangent. If I now draw a continual line coming down, then actually what I have is 45 degrees here, sort of this missing triangle, but I can draw it in. And then this will also be 45 degrees because the angles must add up to 180. So I'm focusing on this purple triangle. And here's the thing, the radius is 1. It is an isosceles right-angled triangle, which means that k to x, this point halfway between L and M, must also be 1. And we can apply exactly the same argument on the other side. And so the answer actually comes out really quickly. It must be that LM is 2. I'm just going to very quickly just go through that again. So we kind of all came together really quickly. But I drew the radii in for these 5 sectors of angle 45 degrees. I then drew a line going down, which would have created another little sector of 45 degrees. I just continued the line until it hits where the line LM. I then argued that this one was 45, this one's 90, so this one must be 45, so it creates this right angled triangle. And because it's isosceles and this was the radius, 1, then this length is also 1. So we've got L to X, make exactly the same argument for the bottom circle, meaning that MX is also 1, and that gives this answer. Really nice method. I actually did this question in a different way, so I'm just going to share it. It's not quite as good, which is why I didn't go for it first of all, but it got me there. So again, I split it up. That is going to be essential into these eights, including this one here. That is 45 degrees. And then I just want to highlight LM. I actually treated LM as the diagonal of a square because I could see there's some symmetry going on. And the reason that I know it's going to be a square, just trying to remember how I did this, is that I've got um, I've got 45 degrees here, so this must also be 45 degrees. And if I have a rectangle with a diagonal at 45 degrees, it's actually necessarily going to be a square. So I tried to then find the lengths of the square. Looking at this green triangle, I know the radius is 1, and because this is isosceles, then I can say that these small lengths are actually 1 over root 2. So whenever you have an isosceles right angle triangle with x and x here, this is 45 degrees, then this is necessarily root 2x. You can apply Pythagoras to get that. So to go the other way, we just divide through by root 2, 1 over root 2, which means the sides of the square are going to be 2 times 1 over root 2, which actually simplifies to root 2. Hence the square has sides, length root 2. But most importantly, I can now draw like half of the square and say I've got root 2 here, root 2 here. What is this length? Again, I can either use the result from above and just times through by root 2 to give me 2, or I can actually do root 2 squared plus root 2 squared. That gives me 4. Square root it gives me an answer of 2. It's a little bit more technical and unnecessary aspects here. I had to use Pythagoras, which I didn't in the first method, but it's still, I think it's still a good one to compare with. Anyway, well done.